Hi, this is Jeff Carpenter. I'd like to talk with you about how you can use Cassandra and DataStax Enterprise for inventory management applications. At DataStax, we provide data management for cloud applications. This applies to a wide variety of use cases, everything from customer experience use cases like personalization and fraud prevention to Internet of Things systems. For this talk, we're going to focus in on how you can use Cassandra and DataStax Enterprise to manage your inventory. You might be asking, what do we mean by inventory? When we talk about inventory, there are two basic types of inventory. The first is what we call physical inventory. This is any tangible object that we could sell, like a car or a Cliff Bar. Let's think about how we might represent physical inventory using CQL. First, we have the inventory of a specific product. We could store the description of the product in the table. Let's assume for right now that we're just storing a product ID. This implies that the product description is available somewhere else. Notice also that the product ID is our primary key for this table. So we'll have a single partition for each product. Next, we have two counts. First is the amount of product that's available for sale and the number of items that have been sold. So in this system, when the amount available equals the amount sold or the amount consumed, we're considered to be sold out of the product. Most inventory management systems are more complex than just selling one-of-a-kind items, but note that this still works if the amount available equals 1. Note there is no reason why the amount consumed can't be greater than the amount available. We could enforce rules about overselling products at the application level rather than at the database level. There's another type of inventory that we need to think about as well. A physical item is tangible. We sell it once. It's shipped from our warehouse, or it goes home in a shopping bag, or it's driven off the lot. But other kinds of inventory are renewable. We sell these products again and again over time. We see this a lot with spaces that we sell for a specific period of time, like a hotel room, or my spare room, or a table at a fine restaurant, or tickets to a football match. Looking at an example CQL schema for temporal inventory, I've kept these same elements from physical inventory, but now I've added a time element. In this case, it's a date. You'll also notice that I've added the date as a clustering key. Similar to the physical inventory table, our temporal inventory has a partition for each product, but the temporal inventory table uses a wide row design, so the inventory for all dates of that product are stored together. A different design approach might be to flip the order of the partition key columns so that data is first organized by date and then by product. The right design depends on the access pattern for your application. Check out our DS220 data modeling course on DataStax Academy for a more complete discussion of Cassandra data modeling. So this is just about the simplest representation of physical and temporal inventory that I can think of. What about some other things that we might want to do? If you're familiar with best practices for Cassandra data modeling, you'll know that query-first design is strongly encouraged. That is, designing tables that directly support queries that will be needed by the application. For an inventory example, it might make sense to obtain information about a product at the same time as we're getting its inventory. That could make for a super fast query. If we want to do that, then we could store product details right in our inventory table. Now, for physical inventory, if we partition by product, we add those columns in as simple columns. But for temporal inventory, we partitioned by a product and use date as a clustering key. So, in this case, we could use static columns to store a single copy of those product details for the entire partition. One problem that we might run into for temporal inventory is that if we are storing a lot of time periods for a particular product, then we might have a partition that's starting to get pretty wide. To keep the performance of our reads predictable, we may want to introduce a time bucket as a way of grouping rows together. The trade-off in this approach is that if we get a search that crosses that time bucket boundary, then we will have to do two queries, one on each partition. There's also a broader context that we will want to consider when dealing with inventory data. I've mentioned previously the idea of product descriptive data being stored separately and inventory referencing products by a foreign key like a unique ID. This allows for a good separation of concerns. You can manage your product catalog separately from your inventory. An inventory management application needs to track the consumption of inventory and usually the ability to return inventory as well. Now, if we're talking about an application in the travel or hospitality domain that's dealing with temporal inventory, we usually talk about reservations, which allow a customer to reserve a space or an asset for some period of time at a particular rate. The rates, again, are often managed by another application. When taking a reservation, the application records the resulting impact on inventory by decrementing the consumed count. Customers can cancel reservations, which would, of course, cause those inventory counts to be incremented again. Now, in the retail world, we're talking about physical inventory. In that case, we're thinking about a customer's shopping cart, which hopefully turns into a purchase order. And again, there is an associated price. Now, there may be a distinction between an order which is in process and an order which is finalized. For example, I may have 5 minutes to complete an order of concert tickets before they are released for someone else to purchase. Now that we understand our problem space a little better, what are the indicators for when using Cassandra for inventory management would be a good fit? The indicators are really the same as they would be for any other type of application. If there is a large or growing amount of inventory data that you need to be available simultaneously in multiple data centers with low latency and always on availability, then Cassandra is a really good fit. Now we'll also talk about how you can build on top of core Cassandra with DataStax Enterprise Analytics and Graph to get real-time insight for more powerful inventory management capabilities. There are a few things that we'll want to think about as we design an inventory management capability, both in terms of the design choices that are available to us within our own systems and the limitations that are placed on us by external systems. It gets fun when we have to think about how we scale up, how to manage consistency on our reads and writes, and how to use mechanisms like transactions, batches, and retries to manage the stability and consistency of our system over time, as we'll discuss in the next few slides. Here is a notional microservice architecture that separates out different types of data into different services for products, rates, inventory, and reservations. We may also have services that implement business processes like shopping and booking. There are also data maintenance applications. These can take a couple of forms. Some of these applications are responsible for synchronizing data with external systems, and these can get fairly complex. We may also have applications that our operations team uses to debug problems or to diagnose customer service issues. If we take a notional microservices architecture, let's talk about the possible error cases that we could encounter around our inventory data and discuss what we can do about them. First of all, we want to make sure that we're not undercounting or overcounting how much inventory has been sold. If our application undercounts sold inventory, then we could actually sell more product than we have. Then we'll need business processes outside of our application to handle that customer service problem. On the other hand, if we overcount how much product has been sold, we can lose the opportunity to sell that product. So there are business costs associated with both undercounting and overcounting sold inventory. We often need to change inventory counts in the context of a larger business transaction, like booking a reservation. If we record a reservation in our system but don't decrement the corresponding inventory, then we have a consistency problem across data types. We can also have consistency problems across systems if our processes for synchronizing inventory with those systems don't work quickly or well enough. So those are a few of the situations that we might have to deal with to make sure our data is consistent. These can arise from errors at the database tier, but also at the services tier and at the boundaries between systems. Thankfully, there are many things that we can do to address those errors. Here are some of the tools that are in our toolbox for providing different levels of consistency for different situations. Some of these are provided by Cassandra, but some of them are approaches that we implement at higher levels of the architecture. At the Cassandra level, we can control the consistency level of our reads and writes to ensure strong consistency of access to individual rows, and even use lightweight transactions for linearizable consistency on individual rows. Moving up a bit, we can get some stronger guarantees across multiple tables with Cassandra's logged batches. As we move up to the service tier of our application, we can use approaches such as retries to work around failures that occur at lower levels. Finally, we can use compensating processes that are both technical and business processes to detect and correct failures. There are some cases where consistency errors are introduced into our systems that we can't detect or don't detect that actually impact our customers. As hard as we may try, these situations can and do occur. Obviously, we want them to be as rare as possible. At this point, our customer service business processes are the last resort. Each of these techniques I've mentioned involves progressively more time to achieve consistency, with more potentially adverse impact on our applications, our customers, and our business. Let's examine some of these techniques in more detail. First, let's examine how we can achieve strong consistency on writes to individual tables in Cassandra. This is our first building block for ensuring consistency in our inventory data. Let's say that we have a replication factor of 3 for our inventory key space. If we have a write that comes into one service instance and we use the quorum consistency level, that means the write is not considered successful until at least 2 replicas respond to the coordinator. Now that third replica might be slow to respond or down, but it will eventually receive the latest copy through Cassandra's mechanisms such as repair or hints. Now if a read comes in to another service instance, we also do a read at quorum. This means that we also need to hear from at least 2 nodes. Now even if one of those 3 replicas doesn't respond to our read or doesn't have the latest data yet, we know that the other one will. Cassandra, in this case, is guaranteed to return the latest data that has been written. Now, if there are cases where multiple instances of a service are competing to update inventory counts, we can use Cassandra's lightweight transactions to help safeguard individual rows. For example, if I have a service that needs to decrement the inventory count based on a reservation, I might want to read the current amount available, calculate the new amount available, and set the available count. But there's a small chance that some other instance could change the inventory count in between the read and the write. We can then use a transaction to say something like, update the amount available for this row, but only if the current amount available is 3. This prevents that intervening write from injecting an incorrect value. Remember that a lightweight transaction only operates on the scope of a single row in Cassandra, so we'll need some other approaches to work at higher levels. Here's one of those, the logged batch. If we have a denormalized table design, it's pretty straightforward to use Cassandra's logged batches to keep writes to multiple tables in sync within a given service. The guarantee of a logged batch is that the statements will all be applied or none of them will be applied. This works well when you have a microservice that is managing these multiple denormalized tables for a single data type. But what about cases where we need to keep changes in sync across service boundaries and across key spaces? One example situation is in booking a reservation. Since the reservation represents our contract with the customer to reserve a specific room at a specific price and with certain conditions, we will mark a reservation as committed at the same time as we reserve the inventory. This is important so that we don't accidentally overbook our hotel. Making the situation more complicated, there could be simultaneous booking and data maintenance activity trying to access that same inventory. Since these types are split across microservice boundaries, there is no transaction mechanism. Since the data is in different rows, and in fact different tables, Cassandra's lightweight transactions are of no use to us here. So we can solve this by a layered approach. Lightweight transactions to protect inventory counts, retries within that booking service, and beyond that, compensating processes to detect and clean up failures. So let's talk about compensating processes. These are processes that are meant to detect and recover from errors that occur in our system at a later time. From a technical perspective, Cassandra's built-in repair mechanisms are a compensating process. We can take advantage of this by running repairs more frequently in order to get data that is more strongly consistent. Note, however, the quorum consistency level approach that I mentioned previously solves the majority of our problem. Another technical approach is to write consistency checking applications. These go in and examine the consistency of our data, perhaps across multiple data types, identifying and perhaps even fixing errors. These require more effort to write, but can be very valuable in maintaining the consistency of the data in our systems. Another recourse that we may have to us is to have business processes that are compensating processes. For example, we may have a customer service application that helps us to rebook customers or to back order products on their behalf, or perhaps to propose a substitute product, or even to issue a refund. Now, all of these compensating processes, once they're exposed to the customer, can have an adverse impact on our customer satisfaction. So obviously, we would like to use those processes as infrequently as possible. To wrap up our thoughts on consistency, let's talk about the larger context of systems that manage inventory. Usually it's the case that there are multiple systems that are tracking our inventory from different perspectives. For example, in the hospitality domain, a hotel will have its own property management system that its hotel staff uses to track who's staying in the hotel and what rooms are available. That's the hotel's perspective of inventory. But typically, the hotel outsources the capability to book reservations to an external reservation system. That reservation system needs its own view of the inventory so that it knows what can be sold. But the property management system is the system of record. It's the final authority on what inventory can be sold, based on what's happening on the ground at the hotel. This is a common system architecture in the hospitality industry. Therefore, keeping inventory in sync across these systems is a frequent issue for a reservation system. For large-scale systems, the main practical approach to keeping data in sync is to use asynchronous messaging between systems. But maintaining consistency across system boundaries is an issue. What if the last room or last item is sold at the same time on multiple systems? This is a consistency problem. I bring this up to note that we often think about consistency as a problem that we have to manage in our own application, forgetting that interfaces with other systems may be another source of inconsistency that we have to address. So the trade-off that we need to make is how much effort to invest in ensuring internal consistency in our system, knowing that external systems may also be introducing inconsistency. The other factor that we balance this with is the cost of not having consistency in terms of customer satisfaction and our remediating processes. One more consideration that's of particular interest for a system managing temporal inventory is how we maintain a rolling window of inventory data over time. Since we have new inventory every day, or even increments smaller than a day, there can start to be a lot of data. While we might want to have a historical record of inventory data over time that we can go back and analyze later, our customer-facing applications typically don't need to access inventory in the past. We could create processes to manually delete obsolete data, but this turns out to be a perfect situation for Cassandra's time to live feature. When we insert inventory data into Cassandra, we could specify a TTL so that the inventory data expires after the time period it represents, perhaps with some reasonable buffer like a day for a hotel room. If we do this, Cassandra will then take care of eliminating the data on the next compaction of those tables, deleting the obsolete data. In this presentation, we've talked about using Cassandra for inventory management in terms of counting the amount of products that have been sold versus what is available. But we can do more than that. There are a number of other use cases related to inventory management that we can start to address when we look at DataStax Enterprise, building on top of core Cassandra. These are use cases that benefit suppliers, distributors, and our customers. For example, using DSE analytics with Spark, we can dynamically identify inventory that's undersold and offer discounts to customers. Using DSE Graph, we can use relationships between people and the products they consume to help personalize shopping experiences and recommend additional products. And we can do this in real time without having to do an ETL to an external system for more analysis. Thanks for joining me for this look at how we can use Cassandra and DataStax Enterprise to manage inventory for your application.